Hi, welcome to today's video on basic architectural acoustics. My name is Arun Iyengar and today we're going to discuss frequency bands and decibel level weightings. So let's begin. We're going to talk about frequency bands first. Frequency bands are used to split the human hearing range, that is from 20 Hz to 20,000 Hz, into smaller bands. This is done because it helps us sort of pinpoint in which frequency range the noise or sound is most dominant, or where the noise is low. Such frequency bands split up the entire human hearing range into smaller bands. One such frequency band system is the 1-1 octave band system. Octave band system basically says that the next center frequency must be double the previous center frequency. I'll tell you more about what the center frequency is. So the human hearing range is totally split into 11 octave bands, starting at the center frequency of 16 Hz band and ending at the 16,000 Hz band. So each band has a starting frequency, an ending frequency, and a center frequency. It also has a bandwidth. The bandwidth is the ending frequency minus the starting frequency. Generally, octave bands are represented by their center frequency. So suppose I say the 16,000 Hz band, I mean that the center frequency of that band is 16,000 Hz. So let's look at the octave bands, the starting and ending frequencies, and the center frequencies. Here you can see the 1-1 octave bands. You can see the starting frequency, and you can see the ending frequency. So here you can see the starting frequency, here you can see the ending frequency, and here you can see the bandwidth. The actual center frequency here is 15.6, but in industry we just use the number 16 Hz band. We call it 16 Hz band, but the true center frequency is 15.6. Similarly, for the 31.3 and the 62.5 center frequencies, we nominally call them 31.5 Hz band and the 63 Hz band. These are only nominal. They are used in industry for ease of use. There's a formula to derive center frequency from the starting and the ending frequency, and there is also a formula to derive the starting frequency given the center frequency and the ending frequency. There is also a formula for getting the ending frequency by knowing the starting frequency and the center frequency. I've told you in the first video that I'm not going to discuss too much mathematics in my videos, so I'm not going to discuss that here. All you need to know is that the human hearing range is divided into various bands called octaves. What we need to understand about octave bands is that the center frequency of one band is double the center frequency of the previous one, or the center frequency of a particular band is half the frequency of the next band. This is what we call as octaves. In octaves, center frequencies are either double of the previous one or half of the next one. So this is what you need to know about octave bands. We are going to talk about the weightings now, the decibel level weightings. You might have heard the terms dBA, dBc, and just dB. So when you use just dB, it means that you're using unweighted levels. You're using the true decibel level that is measured. When you're using A and C weightings, you are manipulating the dB level to get the A weighted value and the C weighted value. So the A weighted value is dependent on the curves near the threshold of hearing. As you can see, in the low frequencies, the human ear is not as sensitive to sound, but in the higher frequencies, the human hearing is much more sensitive to sound. And the C weighting is based on about 100 dB sort of region. So you know this somewhere around this portion. DBC is used in industrial settings where noise levels are higher than usual. The DBA is especially useful for noise levels near residential areas. but the dBc weighting is used in industrial settings. So let's see how to create those weightings. The weightings are there just because the human sensitivity to different frequencies is different. This is the graph of various font levels. This is derived from the equal loudness contours. So I'll just tell you how to calculate the A weighting and the C weighting. So as you can see, this is a graph of A, B, C and D weightings. We're not going to discuss D and B weightings because they are rarely used or not used at all. The A weighting, it gives less prominence to lower frequencies. Hence you can see at 20 Hertz it is minus 50 dB. You have to reduce the decibel level by 50 dB at 20 Hertz to get the dBA level at 20 Hertz. Similarly at 1 kilohertz, there is no change. You don't have to subtract anything, and so on. That's how you get the A weighting. You take the pure decibel level and you manipulate it, you subtract or add certain values to it to get the A weighting or the C weighting. The table for that is here. You can see in the 31.5 Hertz band, you need to get the dBA, you need to reduce the dB value in that frequency band by 39.4 dB. And in the 63 Hertz band, you have to reduce it by 26.2 dB. At 1000 Hertz, it is 0. At 2000 Hertz, the human ear is much more sensitive. That's why we add 1.2. And at about 8000 Hertz, we start subtracting again. So at 16,000 Hertz, we subtract 6.6. This is similarly done for getting the dBc value. This is, I'm not going to involve a lot of math here. So that is a summary of the dBA and dBc weightings. Next, I'm going to show you the octave bands, how they are used in a sound level meter, and how measurements are made using the octave bands. So here you can see my sound level meter. You can see something like a bar chart or a bar graph. You can see the bars moving up and down. These are the instantaneous dB levels on a fast weighting. These bars represent different frequency bands. The first one represents the 31.5 Hertz band, and then the second one represents the 63 Hertz band, and the third one represents the 125 Hertz. The fourth one represents the 250 Hertz band, and so on. And we ended the 16,000 Hertz band. On the right, you can see A and Z. The bars for A and Z are very simple. Usually the A weighting is lower than the Z weighting. Most of the time that is true. You can see that the A weighting is lesser than the Z weighting. The A level is the dBA level, overall dBA level for the entire human hearing range, and the Z weighting is the actual decibel level without any weighting for the entire human hearing range. So I hope this video helped you guys. And one more thing I want to tell you is this is a sound level meter. At the very tip is the microphone, and the main body is the analyzer and the brains of the sound analyzer or sound level meter. One important point to note about the octave bands is there are also 1/3 octave bands, 1/6 octave bands, 1/12 octave bands, and so on. In the 1/3 octave band, each 1 octave band is divided into 3 octave bands, so that totally brings 11 into 3, 33 bands to cover the entire human range in the 1/3 octave band. This gives much more finer detail of the sound. If you need even more finer details, you can go for the 1/6 band octave band or the 1/12 octave band, and so on. And with the weighting, I want to make a note that the A weighting is not always helpful. The A weighting is used by government agencies and some of my clients because that is what the government regulations require. They require the dBA value, but the thing is, low frequencies, especially intermittent low frequency noise, can be very disturbing to people, especially at night. It may cause anxiety, it may cause sleeplessness. So that is one of the drawbacks of the A weighting. If you like these series of videos, please do share, like, comment and subscribe. You can also ask me to talk about a particular topic. If I'm having any knowledge on that, I will definitely talk about it. Please do share that in the comments below. Thank you all, and have a nice day.